Welcome to today's lesson. We are on Unit 3, Curve Sketching, Lesson 1, Intervals of Increase and Decrease. In this unit, we're going to explore one of the applications of derivatives, in which we're going to be able to use derivatives in order to sketch graphs. In this unit, we will investigate and apply the relationships between the derivative of a function and the shape of its graph. We will use derivatives to determine key features of a graph, and we will find optimal values of real situations. So let's get started in how we can look at derivatives to determine key features of graphs and find optimal values in real situations. Let's first go through this investigation together. We are going to investigate continuous increasing and decreasing functions. We're going to use Geometry Sketchpad or GeoGebra to graph the function f of x is equal to x cubed minus 4. And in this case, we are going to use GeoGebra. Now, GeoGebra is a free software that you can use or even download online, and I have included a link for that if you'd like. It's just great for taking a look at the shape of the function. Okay, so what we're going to do here is this is the input bar. So I'm going to put my function as y is equal to x, and hat is the exponent 3 minus 4x. And it usually knows what order it's in. Okay, so there's our function right there. Okay, and we can tell it's a cubic polynomial. Okay, I'm going to change the color of the function. So if I can just select here. It's just to highlight it. We'll change that to blue. Okay, so we've graphed our function. We also want to graph the derivative of the function on the same graph. Okay, so let's do that right here. So y is equal to, by now we should be able to derive fairly quickly. So it is 3x squared minus 4. Okay, and there it is. Okay. Again, I'm just going to highlight this quickly. Okay, so there we have our function. Okay, let's zoom in a bit further. Let's see, I think zooming in would be better. Okay, and let's have a nice close look at it. Okay, so remember that the red is the derivative and blue is our function. So let's take a look at the intervals for which the function is increasing. So here it is. Let's just take the first branch right here. So here the function is increasing. Okay, we're getting bigger and bigger as we go larger and larger in value of x. What is the derivative? The derivative in this case, if you look right here, I can even draw a nice little line if we wanted to. So it's increasing up to this point right here. Okay, so what happens is the function's increasing. The derivative, what values is the derivative? The derivative is positive. Okay, all right, so let's take a look at the next section. The function's decreasing. What happens now? The derivative is negative. Okay, and then we get to this point where it's 0. Well, the derivative changes direction right there. Okay, so without looking at the derivative, if we have the function is then now starting to decrease, so the derivative is still negative, and then we start to increase again. The derivative then is positive. Okay. So I went ahead and changed those lines to nice green lines so you can see the separations of each section of the function. So what can we conclude by investigating this function and the graph of its derivative? Well, we can say that when a function is increasing, the value of the derivative then is positive. Okay. When a function is decreasing, the value of the derivative is negative. Okay. Also taking note that our function is a cubic polynomial, and our derivative again is 1 degree less than the original function. So it's a quadratic. So let's take a look at our first example. find the intervals of increase and decrease of the function f of x is equal to 2x cubed plus 3x squared minus 36x plus 5. So this is how a question would be asked. So find the intervals of increase and decrease of this function. So as you've noticed, I've already put this table here. Now it's easiest in order to find the intervals when using a table. It keeps all of our work very organized, and we can almost see from the table what our function is going to look like. So I've already got that here for you. We're going to use algebra in order to answer this question. So a few key things that we know is that when the first derivative is positive, the function is increasing. Okay, so when the derivative is negative, okay, decreasing. The function is decreasing. Okay. And when the first derivative is equal to 0, when the first derivative is equal to 0, we have a change in direction. Okay, so we have a change in direction. So the first step is to obviously find the first derivative, which I'm going to do we'll say down here. Okay, so the first derivative of our function is equal to 6x squared plus 6x minus 36. Okay, so we want to find where it changes direction. Okay, because that's going to define our intervals. So we would simply now say we're going to set the first derivative equal to 0. Okay, so 0 is equal to 6x squared plus 6x minus 36, and we're going to solve for that. So just factoring out a 6 and dividing both sides by 6, we simply have x squared plus x minus 6. We now recognize this as a simple quadratic. So factoring that, x plus 3, x minus 2. That means we have a change in direction when x is equal to negative 3 and 2. Okay, so that's going to the numbers we're going to use in order to define our intervals. For now, I'm going to fill in everything in the table, but you can take some shortcuts. I'm going to use this color green if you can see it. Okay, so there's negative 3 and x is equal to 2. Okay, we're going to look at the function in between a negative 3 and 2, as well as greater than 2 and less than negative 3. But not equal to, because we know what the function looks like when it's equal to x is equal to negative 3 and x is equal to 2. But for now, eventually you can skip this step and just look for the intervals in between, because you already know what you're going to get in these boxes. Okay, so x is greater than 2, and of course x is smaller than negative 3. Okay, so that's in green. So it shows up okay for you. Okay, so then what we're going to do now is we're going to take values. We're going to pick values, okay, and we're going to sub it into, where do you think we're going to sub it into? We're going to sub it into the first derivative, because the value of the first derivative is going to tell us the characteristic of the original function. Okay, so I just pick values here. We're just going to pick obviously these values, okay, and we already know that the derivative is 0, okay, and that means that we have a flat part, okay, And even if you want to think of this graphically too, when the derivative is 0, okay, if we had a curve such as this, we have a change in direction right there, right? If we were to draw a tangent right at that change in direction, if you think about it, your slope's going to be 0. It's going to be flat right there, okay? And that's why we get the derivative being 0 right at a change in direction, okay, at what eventually you're going to learn to be a maximum or a minimum point of a function. Okay, so let's pick some other values. So x, we're going to say, is -4. Seems like a good number to me. Let's pick my favorite number, 0, and then x is equal to 3. Okay, so plugging it into f prime at x. Okay. And again, you're actually putting in that value for f prime at x. Okay, so you're putting it right back into here. So wherever there is an x, you're going to replace with a -4. And in this case, I mean, you can actually work out the number, but the only thing you care about is what sign it is. Okay, so it is a positive. You only care about the sign. It doesn't matter what the number is. So you can even look at these intuitively. So let's just take x is equal to 0. So this will be 0, 0, and then we're left with a negative number. Okay. Here we're then left with, even if you want to work it out, for completeness, that's positive. Okay, so if the first derivative is positive, we have an increasing function. If it's negative, it's decreasing. Okay, if it's positive, it's increasing. Okay, so for completeness, therefore, the function is increasing when x is smaller than -3 and x is greater than 2, decreasing. And I would like a statement, particularly if it asks for find the intervals. Well, you've showed me in the table, okay, that would be worth some marks for working out the operation, but this is for communication. So you're communicating to me where the intervals of increase and decrease are. There we go. And that would be your final answer. Example number 2. For each function, we want to use the graph of f prime at x to sketch a possible function f at x. So what they're actually giving us in each of these graphs is f prime at x, so our derivative. Okay, so we want to go backwards. We want to actually sketch. Now it does say sketch, so it doesn't have to be completely accurate. We want to sketch an original function. First, looking at A, okay, so we have here is a straight line. So that means that the derivative is constant at -2. So f at x has a constant slope. Okay, so it has a constant slope, which probably means it's linear, which does mean it's linear. And A is a positive. No, it's a negative. Sorry, here. I mistook that arrow as being the derivative, but it's this one right here. So it's at -2. Okay, so the derivative is -2, which means that the function is always decreasing. Okay, so a sketch for this would be something like that. Okay, so it's a linear function. Okay, f x, and again, it's just a sketch, so it doesn't necessarily. You could even try your best to make a slope of 2, so 1/2 up. I think we did a pretty good job there. Okay, so taking a look at B. B, the derivative is positive right here. So positive when x is smaller than 2, and then it's negative. You'll notice it's negative when x is greater than 2. Okay, and at this point where it's 0 is where we're going to have a change in direction. Since the derivative is linear, so a degree of 1, then our original function is going to be a quadratic. Okay, so right here, let's do a dotted line. Okay, so it's increasing. I'm not going to do a perfect sketch, but as long as we put something like this and like that, and we're good. Okay. So in C, we can see that the derivative is never negative, so it's always increasing. It's a quadratic, so it has a degree of 2. That means that our function is going to be cubic. Okay. And here, so what we've got, we know what a cubic function looks like. It's an S shape. And where it's 0 is probably where it's going to do its saddle, where it flattens out. Okay, so I'm just going to go ahead and draw something that I think might look like it. Something like that. Okay, and that looks something like a cubic, and you probably can do a better job than I can right there. Cubic, anyway. So it's be a cubic function. And just to note as well, your saddle should be about at 1, here, positive 1. I sort of shifted it over a little bit more to 1.5. Okay, so let's take a look at D. D is a quadratic, so a degree of 2. So we've got our original function to be a cubic as well. Okay, so we'll do the same kind of shape. However, note that the derivative is negative right here when it's smaller than x is smaller than 1. Okay, positive between 1 and 3, and then negative again when x is greater than 3. In sketching these, I tend to draw dotted lines right through the points where the derivative is 0, and that way that helps me to be able to sketch my graph. Remember, when the derivative is 0, we're going to have a flattening out point. Okay, so the derivative is negative, so it's going to be decreasing. Okay, so this is just a sketch. We're going to be decreasing, and we're going to have somewhat of a flattening out. Then we're going to increase up to here, and then we're going to have another flattening out, and then the function is going to decrease. Okay, and it has that nice S shape like a cubic function. There we go. Example number 3, we're asked to sketch a continuous function for each of the following sets of conditions. So our first part A, says that we have a function that has a first derivative when it is greater than 0. It is greater than 0 when x is smaller than 0. And f prime of x is smaller than 0 when x is greater than 0. F at 0 is equal to 4. Okay, so what this question is saying is that we have one point where the function flattens out. It also increases and decreases. So what function do you know that has those characteristics? Well, it's going to be a quadratic. So the first thing I want to do is actually find this point where it actually flattens out, which f at 0. So when x is 0, y is 4. So it's going to be right there. That's going to be our maximum or our minimum point, or our vertex. Okay, we want to use the proper terms for quadratic. Okay, so when f prime to x is greater than 0, so that means it's increasing when x is greater than 0. X is less than 0. Okay, so here, let's use red. That means over here, the function is increasing because the first derivative is positive. Okay, and we know what it's going to look like, but let's just double check. So f prime of x is negative when x is greater than 0. So when x is positive, so it's going to look like that. Okay, there we have it. And that is f at x.